Hello, this is Kin-Fi Mac from Cornell. So as part of this workshop on quantum oscillations in insulators, I'll actually be talking about a rather non-exotic mechanism of quantum oscillations in 2D insulators that is induced by graphite gates. But I think this is something that is important for people in the field, work in this field to know. And so that's why we actually bring up this talk. And most of the works that I'm going to present was done by my graduate student, Jiacheng Zhu at Cornell. And we also had lots of fun discussion with Andrea Yang from UC Santa Barbara. Okay. So the basic idea is the following. We consider a rather simple device structure that we have a two-dimensional insulator, a very thin film of insulator, usually a few atomic layer thick, that is separated by a metal gate by a dielectric material. Usually we are dealing with hexagonal boron nitride by a distance d. Okay, this is the geometry of the device, and it's actually well known that is discussed by this paper in 2010 that in the low density limit, meaning that when the square root of the density, which is actually roughly equal to 1 over the average separation between the carriers in the 2D insulator, times the distance between the insulator and the gate is smaller than or roughly equal to 1. And we are in the low density limit that the Coulomb interactions between the electrons in the 2D insulator is actually dependent on the geometry of the device. Specifically, it's actually dependent on the distance between the gate and the sample. And as a result, in this limit, the sample and the gate are Coulomb coupled, and we cannot really treat the sample as separated from the gate. In fact, we actually have to treat the sample gate system has to be treated as a single quantity, as a single entity. Okay. So now imagine if you apply a perpendicular magnetic field and there is quantum oscillation that can show up in the metallic gate. And so we actually cannot just consider, the quantum, the chemical potential in the gate oscillates. Actually, because of the Coulomb coupled system, the chemical potential in the 2D insulator also oscillates due to the magnetic field. And as a result, it actually gives rise to a rather general phenomenon that when the sample is coupled to a gate in a short distance, we actually can observe quantum oscillations in the insulating state. So this talk, I will be just giving two materials example to illustrate this general phenomenon. I'll be first talking about Moire materials with small energy gap. And then I'll be talking about a monolayer of tungsten telluride that is a small gap Ti, topological insulator. We also observe similar kind of oscillations near the charge neutrality point of this material. Okay, first talking about a semiconductor Moire systems. You can actually form a Moire superlattice structure by putting two monolayers of semiconductors on top of each other. One example would be, for instance, tungsten diselenide on tungsten disulfide. And because of the natural lattice mismatch between these two different materials, and if you just align the two materials at 0 degree, and it forms a Moire superlattice structure that looks like this. And so the presence of the superlattice structure will give rise to extra Bragg reflection for the electrons. And as a result, it forms electronic mini bands. They are called Moire flat bands that can enhance the Coulomb interactions between the electrons in the system. So we are dealing with a mini Brillouin zone because of this superlattice structure and Moire flat bands. And this is so this is the device structure. We have a graphite gate. We have this Moire system that as the 2D insulator that is spatially separated from the gate by hexagonal boron nitride with a distance about 5 nanometer. Okay. And this is an example of the measured resistance as a function of gate voltage that you apply to change the electron density of this 2D insulator of this sample. And we can easily identify two resistance peaks in this plot. The first is the resistance peak at filling factor 1, and the other is the resistance peak at filling factor 2. And just to make the long story short, the filling factor 1 peak is corresponding to a half-filled Moire flat band. So it's actually a correlated Mott insulating state. And for filling factor 2, on the other hand, it corresponds to a fully filled Moire flat band. And as a result, this is of a single particle origin. It's just a simple band insulator. And there's nothing exotic about it. And so as a result, we would just focus on the filling factor equal to 2 peak. But we actually observe, we observe similar thing even for the filling factor equal to 1 MOS state. So here, let me just zoom into the filling factor 2 peak. This is again resistance versus gate voltage. This is the filling factor 2 peak. And we park at several specific filling factors that's shown by the arrows here near this resistance peak. And we measure the resistance as a function of the perpendicular magnetic field. And you can actually clearly see quantum oscillations in the insulating state, right? Actually, the larger the resistance, the clearer the quantum oscillations. When you tune the filling factor away from the filling factor 2 peak, and the oscillations just disappear. You can also increase the temperature. When you increase the temperature such that the oscillation in the graphite gate disappear, the oscillation in the sample also disappear. And I'm showing here only for the filling factor equal to 2 resistance state, but we can also observe similar oscillations for the MOS state. Well, we also study the effects of the gate material because we think that the graphite gate is so important in terms of giving rise to these quantum oscillations. And so on the left, we actually examine a device, well, basically the same device, that the moire material is actually coupled to the graphite gate, and we just see quantum oscillations in the insulating state, the filling factor 2 insulating state. On the right, we actually make another device. Instead of using graphite gate, we use a tantalum selenide gate. Tantalum selenide is a van der Waals metal with much higher band mass than graphite. So under the studied range of the magnetic field, we don't see clear oscillations. We don't expect clear oscillations from this metallic gate. And in this case, we actually can clearly see that there's no quantum oscillation observed in this insulating state. So short message, quantum oscillation can only be seen in devices with the gates that only show that can show quantum oscillations. So then it comes to the second example of my talk. I'll be telling you about a monolayer tungsten ditelluride. The motivation of this talk is actually from this recent paper from the Princeton group. So we are actually looking at a device structure that's exactly the same as the Princeton group does. This is the device structure. We have a tungsten telluride layer embedded between top and bottom gates. Both are graphite gates. The top gate has a smaller distance to the sample, so we expect actually stronger coupling between the sample and the top graphite gate, and the bottom gate is basically far away from the material. Monolayer tungsten telluride is a TI. So as a result, in order to fabricate this device to measure the bulk conduction, we just basically have to fabricate a carbonyl disc device. And to do that, we make one of the contacts to actually not touch the edge of the device. So it's really, we are measuring the bulk conduction through the TI. Different from the Princeton group, what we have done, actually one extra thing we have done here is to put electrodes onto the top graphite gate, so we can perform independent transport measurement on both the tungsten telluride layer and the graphite gate layer. Okay. And this is the measured 2-point resistance of the tungsten telluride layer as a function of the top gate voltage. And you can see a big resistance peak. Basically, that's corresponding to the gap region of the topological insulator, that when you tune the Fermi energy into the gap of the TI, it shows up the large bulk resistance in the sample. Okay. And well, if we fix at a particular gate voltage that is near the gap of this TI, we can actually reproduce the quantum oscillations that's seen by the Princeton group on the tungsten. When we measure the tungsten telluride resistance, you can see the clear quantum oscillations in this case. Well, the interesting thing here is that actually we can also measure the graphite gate resistance at the same time, right? Then we can actually compare the two resistance together. And this is the quantum oscillation of both the tungsten telluride layer and the top graphite layer subtracted by a smooth resistance background. So you can actually see that the oscillations of both the top gate graphite and the tungsten telluride, they actually match with each other very well. And a better way to show this is in this contour plot. What we do here on the left is the tungsten telluride resistance. On the right is the top gate graphite resistance. And because we have two gates, we can actually keep the tungsten telluride at a constant density that is very near to its energy gap. And what we change here by the top gate here, we also correspondingly change the bottom gate such that we only change the electric field in our field effect device so that only the density in the top gate graphite layer is varied, but the density in the tungsten telluride layer is fixed. And you can actually see that in this case, because of the changing density of the top gate graphite, the Landau level actually disperse with the applied gate voltage. And you can also see very similar dispersion measured in the tungsten telluride layer. And in fact, you can actually find the Landau fans for both of these layers, and they match very well with each other. And they also both actually originate from the same origin, which is actually the charge neutrality point of the top gate graphite. Okay. All right, so I hope by this point I convinced you that at least we have to be carefully thinking about the coupling between the sample and the gate in terms of studying the quantum oscillation in a 2D insulator. So to end this talk, I will just provide a possible microscopic mechanism why we actually can see such a quantum oscillations in the 2D insulator when it's coupled to the graphite gate. And it's actually quite well known in the optics community, maybe less known in the condensed matter physics community, that the energy gap of a two-dimensional insulator is actually very sensitive to its dielectric environment, because this charge gap for charge excitation is strongly dependent on the dielectric constant of the surrounding environment. And actually, a recent experiment from our group has shown that, so this is the device structure of our experiment. We have a 2D semiconductor that is Coulomb coupled to a graphene layer separated by a very thin hexagonal boron nitride layer. And when we tune the density in the graphene layer, and at the same time we measure the energy gap of the 2D insulator using optical spectroscopy, we can actually a strong renormalization of the energy gap of this 2D semiconductor when we dope the graphene layer. So, and this is the graphene Dirac point. So this really illustrates, the importance of dielectric screening on the 2D insulator energy gap. So now when you imagine you apply a perpendicular magnetic field to this system, which you actually will drive the graphene into compressible and incompressible states when it successfully fills the Landau levels. And when the graphene is in the compressible state, you will get actually a more efficient screening and a smaller energy gap on the 2D insulator. On the other hand, if you actually, the Fermi energy in the graphene is in between the Landau levels, then it's in the incompressible state, it's inefficiently screened. The Coulomb interactions in the 2D insulator, we actually get a larger gap. So as a result, because of the quantum oscillations in the energy gap due to this periodic screening from the graphite layer, we actually expect that the resistance, no matter what kind of mechanism, either thermal activation or hopping transport, the resistance will oscillate together with the graphene layer. Okay, to conclude, we actually want to say that quantum oscillation in 2D insulator when it's coupled to a graphite gate is a very general phenomenon. So we actually have to be careful in terms of studying, in terms of interpreting the quantum oscillations near the charge insulating gap. And what we also provided one possible mechanism is basically that the oscillation in the 2D insulating gap induced by screening from the graphite gate. And with this, I thank you for your attention.